So hello everyone, today we will continue in chapter 4, the Fourier Transform part 2, and we'll start with some summation formula. So if f belongs to capital F, class capital F, then these sums are equal. Proof. First suppose that f belongs to fa for some a positive and let b between a and 0. Now the function 1 over e to the power 2 pi I z minus 1 has simple poles with residues 1 over 2 pi I at each n in z. You can check by yourself, and consequently the function f of z over e to the power 2 pi I z minus 1 has residues f of n over 2 pi I at each pole n in z. Now consider the following contour omega n containing the integers from minus n capital till n in the following direction. Using the residue formula, we have integral over omega n of the function f of z over e to the power 2 pi I z minus 1 dz is equal to what? Equal to 2 pi I times summation of the residues at the poles. We have the poles are inside this rectangle minus n plus 1 till n. So summation between minus capital N and n residues are equal, as we said, f of n over 2 pi I. This 2 pi I cancels out with this 2 pi I, and we conclude that this integral here is equal to what? Equal to the to this summation. Now, since we have f is of moderate decrease, as we said here, then this series converges, and we conclude as n capital tends to infinity that this series is equal to what? Equal to the integral over L1 of f of z over e to the power 2 pi I z minus 1 dz is minus the integral over L2. One can simply show that the integral over the vertical segments is equal to 0. We did this thing many times, I will not repeat. So minus integral over L2 of the function f of z over e to pi I z minus 1 dz. Of course, L1 is the real line shifted down by b. L2 is the real line shifted up by b. Now, recall that if modulus of w is greater than 1, then 1 over 1 minus w, then 1 over w minus 1 is equal to what? Equal to w minus 1 and 0 till infinity of w power minus n. And we have e to the power 2 pi I z in modulus is greater than 1 on L1. Then we conclude that on L1 1 over e to the power 2 pi I z minus 1 is equal to e minus 2 pi I z multiplied by summation from n equal to 0 to infinity of e to the power minus 2 pi I n z. Also, we have if modulus of w is less than 1, then 1 over w minus 1 is equal to minus summation from n equal to 0 to infinity of w power n. And on L2, if you consider e to the power 2 pi I z in modulus is less than 1, so you conclude that the term 1 over e to the power 2 pi I z minus 1 is equal to what? Equal to minus summation from n equal to 0 till infinity of e to the power 2 pi I z n on L2, of course. Now, we conclude that the summation over z of f of n is nothing but integral from L1 over L1 of f of z, replace 1 over e to the power 2 pi I z minus 1 by this term here, e minus 2 pi I z multiplied by this sum, plus integral over L2 f of z multiplied with this sum. Now collect everything and reduce, and we can, due to the convergence, interchange the summation and the integral, and so we get this is equal to what? Equal to the summation from n greater than or equal to 0 over of integrals over L1 of f of z e to the power minus 2 pi I into n plus 1 z dz plus integral plus summation from n starting from 0 to infinity of the integrals over L2 f of z e to the power 2 pi I n z dz. Now we can again shift the curves L1, sorry, the sets L1 and L2 to the real line. You get summation from n equal to 0 to infinity of integral from minus infinity to plus infinity of now z becomes real, equals to x e to the power minus 2 pi I n plus 1 x dx. This is nothing but f hat of n plus 1 plus summation from n equal to 0 to till infinity of integrals from minus infinity to plus infinity of what? Of f of x e to the power 2 pi minus 2 pi I of minus n z x dx. This is nothing but f hat of minus n. We end up with summation from 0 to infinity of f hat of n plus 1 plus summation from 0 to infinity of f hat of minus n, and this is equal, combining the sums to the summation over the integers of f hat, and we are done. This is the Poisson summation formula. Now, very important to hit the very important result, Paley-Wiener theorem. So before starting with Paley-Wiener theorem, we'll say this theorem, which is the converse of the first theorem took in this chapter. So suppose that f hat satisfies the following decay condition, as you see here, for all xi belongs to R, and for some, of course, small a and capital A positive. Then f of x is the restriction of some holomorphic function in Fp for all b belongs to or between 0 and a. Now, Paley-Wiener theorem goes a step further than the previous theorem and describes the nature of those functions whose Fourier transforms are supported in a given interval, for example, minus capital M plus capital M. So, the theorem says, if you have f, or suppose that f continuous of moderate degrees on R, then f has an extension to the complex plane that is entire with the following decay condition for some capital A and M positive, if and only if f hat is supported in the interval minus mm. So we will prove first the easiest direction, the second one. So suppose that f hat is supported in minus minus mm. Now consider the following integral. Now f of x is equal to the integral from minus m to plus m of f hat psi e to the power 2 pi I x psi d psi. This is the Fourier inversion formula, as we said. Consider the function g of z equals to the integral from minus m to plus m of f hat psi e to the power 2 pi I z psi d psi. Now this integral is well defined, so g is well defined since the range of the integration is finite. And it's crystal clear that g of z is equal to f of z when z is real. Of course, we also can show that G is holomorphic by a theorem we took in chapter 2, starting with suppose that f defined on omega cross z1 is continuous in both arguments and holomorphic, etc. You can review this theorem and use it here to show that G of z is holomorphic as required. Now, finally, we show that G of z, the extension of f, satisfy the decay condition in the theorem. So let's erase here. Modulus of G of z is less than or equal to the integral from minus m to plus m of what? Of f hat psi psi e to the power minus 2 pi psi y d psi. Now, since f hat is of moderate decrease, this is less than or equal to what? A e to the power 2 pi 2 pi. And now psi between minus m and m, so we take, since we have minus sign here, we take 2 pi m y, and y is of course less than modulus z, so we are done. Now the converse result requires a little more work. So the proof done in 3 steps. So first, step 1. Now we are proving the first direction, and the proof is done in 3 steps. The step 1, assume that f is holomorphic in C, f is an entire function satisfying the following decay condition in X and growth in Y. So the condition is a star, modulus of fx plus iy is less than or equal to what? A prime e to the power 2 pi m y over 1 plus x squared. Okay, now we then prove under this stronger condition. Of course, this condition is stronger than the condition presented in the main theorem of Paley. So we'll prove that under this condition that f hat psi is equal to 0 if psi is not in the interval minus mm, so if psi is modulus or an absolute value is greater than m. Now, then in step 2 we are going to relax the condition, or in the next steps we are going to relax the conditions to finally show the theorem whenever the main condition or the main the main condition holds. Now suppose that psi first greater than m, and write f hat psi equals to what? Equal to the integral from minus infinity to plus infinity of f of x e to the power minus 2 pi I psi x dx equals to what? Integral from minus infinity to plus infinity of fx minus iy e to the power minus 2 pi I psi x minus iy dx. Now, so we shifted r downward by y positive. Okay. So f hat psi is less than or equal to what? Integral from minus infinity to plus infinity of uh, modulus of x minus iy times modulus of e to the power minus 2 pi I xi into x minus iy dx. This is less than or equal, using of course the condition here star, you call the star. So less than or equal to a prime integral from minus infinity to plus infinity of e to the power 2 pi m y minus 2 pi psi y over 1 plus x squared dx. This is less than or equal to what? C e to the power 2 pi. C is of course a positive constant. 2y 2 pi y m minus xi. Now m minus xi of course is negative, since initially we supposed that xi is greater than m. So this term here is negative, and letting y tends to infinity, this terms goes to 0, and we conclude that f hat psi is equal to 0 whenever xi greater than m. Now we can do similar argument, or we can apply similar argument or similar reasoning to show that f hat psi is equal to 0 whenever xi less than minus m, by shifting now the real line up by y positive to get f hat psi is equal to 0. So I'll not do this thing. You can do it by yourself. Now we get into step 2. In step 2, we will relax the condition star by assuming only that f satisfies double star, which is f of modulus of f of x plus iy less than or equal to what? A e to the power 2 pi m modulus of y. This is still a stronger condition, in fact, than the main condition in the theorem, but it's weaker than star. So first, suppose that xi greater than m, and consider the following auxiliary function f epsilon, for epsilon positive of course, f epsilon of z equals to what? Equal to f of z over 1 plus I epsilon z power 2. Of course, we have as epsilon tends to 0, f epsilon z tends to f of z. F epsilon z tends pointwisely to f of z. Okay, now the term. Okay, the term 1 over 1 plus I epsilon z power 2 has absolute less than or equal to 1, in fact, in the closed lower half plane, including the real line r. Okay, so in the closed lower half plane here, including the real line, no, this term here is less than or equal to 1, or has absolute value less than or equal to 1. You can check it by yourself. Also, we have f hat epsilon of xi tends to f hat of xi as epsilon tends to 0. But now for each fixed epsilon positive, we have f epsilon of x plus iy is less than or equal to what? F of x plus iy over modulus of 1 plus I epsilon z power 2. This is less than or equal to what? A e to the power 2 pi m y using double star, of course, over modulus of 1 plus I epsilon, replace or substitute, replace z by x plus iy. Power 2. This is less than or equal to what? A prime, some positive constant, e to the power 2 pi m modulus of y over 1 plus x squared. And now by step one, f hat of psi is equal to 0. F hat psi is equal to 0. F hat psi of epsilon is equal to 0, and letting epsilon tends to 0, we conclude that f hat at psi is equal to 0. Okay, this is for psi, supposing psi greater than m. Now, if we suppose that, I don't know, I'm not sure if okay, I wrote here psi greater than m. Now, if psi is less than minus m, we can do similar argument, although we must now argue in the upper half plane and use the function 1 over 1 minus 1 over 1 minus I epsilon z power 2 instead of this function. Okay, so now step 3 actually, to conclude the proof, it suffices to show that double star can be obtained from the initial condition of the theorem, and we will conclude the proof after proving the following result. So theorem, suppose that capital F holomorphic in the sector Z such that principal argument of Z, capital A arc Z, is less than or between minus pi over 4 and pi over 4. So this sector is actually nothing but this. Okay. Okay, now F is holomorphic in this sector and continuous. Suppose that F is continuous on S bar, the closure of S. Also suppose that modulus of F of Z is less than or equal to 1 on the boundary of S. So the boundary of S is denoted by del S. And modulus of f of z, a lot of assumptions, is less than or equal to capital C e c e power small c modulus z for all z inside S. So this boundedness condition on the boundary, this is in the interior, continuity on the closure, and holomorphic in the sector. So we have 1, 2, 3, 4 conditions on this function, on this capital function f, on this function capital F. Of course, here C capital is positive, here C is positive, also small c is positive. Now, then, you conclude that after all these assumptions that modulus of f of c is less than or equal, in fact, to 1 inside z, in S, inside S, sorry. Okay. Now, in other words, if f is holomorphic in S and continuous in S bar, and if f is bounded by 1 on the boundary of S and has no more than a reasonable amount of growth in S, then f is actually bounded in S by 1. So this is what the theorem is saying. Okay, now proof. So in brief, one modifies EZ square by replacing it by z power alpha, by e to the power z power alpha, e power z power alpha. With alpha less than 2, we can assume that alpha is equal to 3 over 2 for simplicity. Now, if epsilon positive, suppose that epsilon positive, and consider the function f epsilon z equals to f of z e to the power minus epsilon z power 3 over 2. Now, if we suppose that z is equal to rei theta, theta belongs to minus pi pi, so this is the we are working in the principal branch, then z power 3 over 2 is nothing but 3 r power 3 over 2 e to the power I 3 theta over 2. Hence fe is holomorphic. Fe is holomorphic, or f epsilon, sorry, is holomorphic in S and continuous up to its closure, up to S bar. Also, modulus of e to the power minus epsilon z power 3 over 2 is equal to what? Equal to e power minus epsilon r power 3 over 2 cosine 3 theta over 2. Now, in S we have theta between minus pi over 4 and pi over 4. So 3 theta over 2 is between minus